So I just want to give everybody a warning that I've done several practices today of these slides, and not one has gone well. I'm always running out of time. I get very panicky. Expect that at some point. I might stop making sense. Whoa. Already. Okay, we got that out of the way. So I'm just going to go and start because I can kind of do the introductions in this first 20 seconds. So the talk is going to be on just decision tree algorithms, very clever name that Hannah helped me come up with, And it's going to be kind of, I want to introduce decision trees. I want somebody that doesn't know about decision trees to be able to understand what the whole algorithm is about. So first, we're going to go through an example of how a single decision tree is grown, the algorithm behind it. Then we're going to talk about the drawbacks of only using a single decision tree in your end model. And we're going to go over some popular decision tree algorithms in practice. So here's an example of a decision tree, in case you weren't aware of one. This is my cat. You can see the mouse, right? Yeah. His name is Raiden. So this model is determining if he's going to sit or not. No sits. Thank you, Hannah, for making me the decision tree. So if there's a box and he fits, he's going to sit in the box. So our toy machine learning task is going to be predicting if somebody's going to survive a confrontation with a bear. And we're given a data set for this. The features are going to include the type of bear, the days since the bear's last meal, and whether that person owns a cat. So this is, here is our toy data set. As you can kind of just see, encounter number 3, there was a black bear. It was 7 days since his last meal. He does not own a cat. And yes, the person survived. So we want to predict this last one. We don't know if this person survived or not, but we want to know what the data is going to tell us about this person's follow rate. So the first thing you do in machine learning, and let's take a data-driven approach here. What does the data tell us? We don't want to go in with any assumptions. We want to forget everything we know about bears or hunger or cats even. We just want to see what is there in the data that's going to tell us this unlucky encounter number 14. So let's go over how we're going to do that, how we're going to grow a decision tree. So the first thing that we need to do is we need to define a metric that's going to tell us how good a certain split of the data is going to be. Intuitively, your best splits result in 2 subsets with pure classes. That's the goal, pure classes. So the more mixed up a class is, the worse of a split it is. Then we're going to try a whole bunch of different splits at one point. And we're going to score them. We're going to take the best one, and then we're going to get 2 new nodes, and we're going to kind of repeat this for all of the new nodes. The stopping criteria is that if a node is pure, then we're not going to, there's no more work to do because we've defined those classes perfectly. And then we're going to profit, number 5. So here's a sample of a split on our original data set. The bear type of polar bears are on the left, the non-polar bears are on the right, and I've color-coded the classes. So as you can see, this does a pretty good job of splitting the data. We have 1 misclassified one on the left and 2 on the right. So there's a little bit more work to do. This is another split candidate. It's the days since the last meal being less than 11. This split is not quite as good. The left kind of data subset here is not as pure as the one before. So we're going to go with the polar bear split. So that's how we grew the first node of the tree, and now we're just going to do the same thing for the other 2. So let's go through an example on the left. We notice that if the days since the last meal are greater than 25, then we can separate those 2 things. And on the right, owns a cat is actually useful in this case. We're going to say if he owns a cat, then we're going to split that data. Just by inspection, because I don't want to go through all these steps, and it's kind of a silly example. This is the final tree that we would arrive at with this data set. You'll notice that our toy example it actually did matter in the end if he owned a cat. He survived because of it, in fact. So this leads us to kind of the downfall of just using one decision tree. There are going to be biases in your data, and they are going to kind of bias your data in one certain direction. And using only one decision tree, you're going to really be subject to a lot of those biases. And it's going to be hard to kind of rely on your end prediction with that in there. So an additional fault of using a single decision tree is it really doesn't fully make use of all of the features in your data. So once you make that first split, now those two branches aren't actually talking to each other anymore. They don't really find relationships amongst the two branches. The further you go down, the more distant your data sets get. So you find patterns that really aren't relevant to the whole thing. So our solution, let's just create a whole bunch of trees, find some way of making them diverse. So we're actually getting different trees, not just the same tree, and then figure out a way to kind of combine all of their predictions together so that we can kind of cancel out some of those biases that any single decision tree comes up with. So simple approach to this is random forests. How are the trees grown? How are they grown diversely? They take each tree is grown with a subset of the data, a random subset of the data. So no tree sees the same data. At each split, we're only going to look at a subset of the split candidates. So we're also not going to get every possible combination there. So here's an example of random forest, and then all their predictions are added together. So you can see here, this decision tree down here really thinks cats are important for your survival. Oh, I screwed it up, I clicked. Okay, this is going to be a long slide. So we're going to really go into this cat survival thing. So we have this bottom left tree who really likes, or who really does not like cats for your survival. This one, you must have a cat to stand any chance of survival, is also a decision tree that can come out of it. It's kind of related to our first one, but you're not going to get, so those two biases are going to cancel out when you average them. But let's go to a little bit more complex. Let's go, what do actually people use in practice? XGBoost and LightGBM are both widely used to win machine learning competitions. And it comes up with a technique to better diversify your trees. In that it trains on the gradients. The errors of your previous tree is the point that I wanted to get at. It's also a very confusing topic. I did put a link to a good explanation of it. I have some time on this slide because this is just a double 40-second slide. So let's review decision trees. They're great at capturing interactions between features. They're very intuitive, which is my favorite thing about them. I can actually understand what it's learning. They're great for ensembling with neural networks because the learning style and the learning kind of algorithm is very different. And let's go through some, I do want to mention CatBoost. I didn't mention in this presentation so far. It was a mistake. But CatBoost is a categorization kind of decision tree model that's much like XGBoost and LightGBM. Here's my other cat, and my other cat. It's sitting down. So, all
right, let's thank Matt.
Thank you. I almost pulled it together there. Almost pulled it very good.
So yeah, as you can see, it's pretty tough to give one of these smoothly. So do we have any questions for Matt?
And I'm happy to answer any more advanced questions about XGBoost and LightGBM because I researched those a lot before I realized I had no time to go into them.
Would you be able to explain the gradient boosting part of the?
It's a little bit challenging to explain, but I can kind of give you a high overview because it's challenging to explain because I don't fully understand it. So I don't want to speak about this. There's a great blog post that is linked here, but essentially, in XGBoost and LightGBM, you're not fitting to classes anymore. You're fitting to scores. So it's going to make a one versus all decision tree. It's like, let's say you've got 10 classes and you want 100 iterations of this. It's actually going to train 10 trees in the first iteration, one for each class. Then it's going to train another 10 trees. The outputs of each of these trees is going to be a score of how likely is it to be that class if it follows this method down. All of those trees are added together to kind of get the prediction at that point. That's compared with the actual ground truth prediction, and there's going to be a difference there. That's the residual. That residual is actually input to the next model as the data. Like, you don't train on that original data anymore, you actually train on the error. So every single decision tree is just trying to predict the errors that the other tree was making. Does that make sense?
Is there any sense in trying to mix these with like spatial trees, like R trees or quad trees or something like that, along with decision trees?
Can you define what those are? Because I'm not familiar with those ones. I don't think your mic is on.
Take that offline.
Sure.
What would be an alternative to decision trees? Next best option?
Well, I mean, neural networks are great, but I don't see any reason why you wouldn't want to use an ensemble with both of them. As long as you can kind of like form the data in a good way for both the tasks, they're really complementary. They're kind of independent learning techniques, so.
So it seems like GBM is becoming like rapidly overtaking XGBoost as the popular choice.
Yep.
Why is that? What are some of the advantages of like GBM to XGBoost?
Okay, so there is one common misconception. I want to kind of get to where they're similar first, and then we'll get to where they're different. The one misconception is that light GBM trains trees in a kind of a depth-wise first approach. That's not exactly true. It essentially looks at all of the possible nodes, all of the splits there, and chooses the best one. So it's not constrained to do level by level growth that XGBoost is associated with doing. That is the default parameter in XGBoost, is kind of level-wise growth. So you'll first do the top node, then you'll do the next two nodes, and then you'll kind of do the nodes after that. But there are options in XGBoost to actually do the same training that Light GBM uses. Light GBM is a lot faster. I don't know exactly how they are faster. The differences in the techniques is Light GBM has a method for subsampling. So rather than randomly subsampling your rows to kind of train a new decision tree, it actually looks at the residuals and kind of grabs the entries with the higher residuals more often than the entries with the lower residuals. So that's one way it kind of speeds up its training. And another one is in really sparse feature spaces. If two features never co-occur at the same time, then there's like an efficient way of actually combining those features together. I don't understand that, but that's one of the ways they're different. I don't know. Yeah. Is there a green light? I think you need to hold it down to turn it on.
Testing. Oh, well, that was fine. So feel free to like punt this to Beers, but since you're a fresh expert on this, I mean, I know there's a lot of regularization that goes on in these. Can you give me like a rough intuition as to what that looks like, and if there's any difference, in particular XGBoost, Light GBM?
I don't know that much about this topic, because it was at this point that I realized I was going way too deep into this subject. But I do know that that's one of the biggest improvements that XGBoost has over kind of some more other implementations, like scikit-learn has a gradient boosted tree that just doesn't perform nearly as fast or as well as XGBoost. And they attribute that to the regularization that they use to train the trees. I don't know what the exact algorithm is behind that. But yeah, there's a lot of good resources online to read about that.
Of the two things that you said you really wanted to be asked the question, tell us the top two things you want to tell us.
Sorry? Oh, that I was afraid of being asked? That I wanted to have asked? Yeah. Well, I definitely wanted the thing about the light GBM and the XGBoost about the way the trees are, the way the splits are chosen. So I already kind of fished that into one of the answers, even though I wasn't explicitly asked that. That was really the only one. I don't have a good answer for you, sorry. Oh, actually, I do have a good answer for you. Often people will ask, what should I use, Light GBM or XGBoost? And I have read a lot of the posts that I was, when I was researching this, those are the questions I got asked, or those are the kind of blog posts that I read about. And there really doesn't seem to be a good answer. Light GBM is definitely faster, but when you look at a lot of the results, they kind of can go either way. So I think the best approach is just to use both. They're both really easy to implement, and they're both continuously being worked on. So it might be that Light GBM edges out XGBoost for a little bit, but XGBoost is kind of being updated regularly, so it's going to edge out this kind. They're going back and forth in a battle right now. So, yeah.
Is it possible for these to scale up to massive data sets and parallel computation? And how does that look?
They both use parallel computation. The trees are grown sequentially, but the operations inside of growing one tree can be parallelized, like finding the best split, stuff like that. One of the biggest selling points is how they can handle massive data sets. I'd like to be able to argue that a little bit better, but I can't confidently. Okay.
We've got a couple more minutes if anyone else has a question. Oh, okay.
Could you explain the difference between Gini and information gain in terms of split criteria?
Yeah, I actually had I used to have math in these slides, and I took it all out. I can define the Gini index like using math, or like the intuition behind it.
Which one do you pick?
Oh, I don't think you pick either. You just use XGBoost, which kind of does that for you. But most of the times, Gini index is probably a little bit simpler. It's just, I don't really want to go into the math right now. Gini index and information gain. Those are like the two most common. I think XGBoost and Light GBM don't use those. Like they use something that kind of tries to approximate those. Yeah, and they try to approximate information gain. So that's probably your answer. Information gain is probably better.
Sorry, I don't know if you have kind of seen the same problem with the scikit-learn. I'm not sure if the XGBoost actually solved this, but have you noticed that, is it hard or easy to find cross-feature, say, A minus B, like x1 minus x2, as a distinguishing feature in decision trees? I'm not sure if XGBoost is solving this.
No, I don't. When I was researching that, I did hear, in theory, there are some trees that are able to kind of use those kind of simple relationships as features, but I do not think that XGBoost or Light GBM implement those. So that would be one of the weak spots. Yeah, you might want to just increase your feature set so that you have all of those combinations as features.
My turn? I think this works okay. I wanted to go back to the question that Bill asked and just explore that a little bit deeper, like what's the alternative? And the alternative is a neural network. And faced with a problem, when do you pick one or the other? If you have the luxury of doing both and ensembling, fine. But I remember seeing discussions, and this is kind of for the room as much as for you, but what criteria, what characteristics of your data would lead you to go to a decision tree versus a neural network? So for example, it may depend on how much data you've got to train a network, right? You may not have that much, whereas a decision tree will give you an answer with a relatively smaller number of data. Are there other things that you know of to make that choice?
This is kind of a wishy-washy answer, but whenever I kind of see a new machine learning problem, I kind of try to think about how I would solve it. And if I see a lot of kind of like, well, if it's this case, then it's going to kind of go down here. Like if I can kind of see the solution kind of working out in the way that decision tree could, then I would say decision trees are probably pretty good. A lot of language, I think, is really good with decision trees, classifying if this word's in it, or if both of these words are in it, then it's going to be this one class, stuff like that. Yeah, I would love to hear what anybody else has on this topic, if we can kind of open that up to the floor.
We've kind of run out of time. So maybe we can have a continuation of this conversation over beer at Rogue afterwards?
Yes.
All right. Thanks, Matt.
No worries. I actually...
Bruce, am I audible?
Yeah, it's coming to slides. So
That's probably right. So totally fine.
That's right.
Good from here?
Yes. I think I do. So does this give you the two-screen view, like the presenter's view?
I think so, yeah.
Okay.
Present there. And I think I turned off the first time, yeah.
What's I'm sure?
Oh, you went back, yeah, okay.
Oh, the keyboard changes. Okay.
Yeah. Ours is very smart. Our other cat is very
Anytime, Aanchan.
Hey, good to start.
Go for it.
So, wait, why is that showing up?
I'm not sure. Just click the play button.
Wait, one sec. Okay.
Can you click on the...
Wait. I can't quite see it.
Does anyone know MacBook Pros really well?
Yep, I did it. Okay, so we're doing an introduction to chatbots. My name is Aanchan Mohan. And I call it as a modest introduction. At some point, we should switch slides. I don't know why it's not switching.
The first one you need to hit.
So I'll go over the background a little bit. So examples and a brief classification are there. You can have task-oriented dialogue agents. They're designed for a particular task, and they're set up to have short conversations. So this could be Alexa or Google Now, or chatbots in general, which are set up to mimic unstructured conversations or chats characteristic of human-human interaction. A turn in a dialogue essentially consists of it's like playing a game. A conversation consists of you say something and I say something. Siri in 2017 can do about 2 turns, which is you can ask it a question and then ask a follow-up question. Chatbots, though, require you to have multiple turns. So this is mimicking a natural conversation. So this is a well-known chatbot called Cleverbot. But one of the first chatbots was one called Eliza. And here's the distinction between AI and machine learning. Eliza was a chatbot which was a Rogerian psychologist, and it essentially consists of pattern transform rules. So any text that would come in, it would transform it. So you hate me would transform into what makes you think I hate you. Of course, learning rules from chatbots in order to reply is a bit tedious. So you'd want to be learning these rules directly from data, and that's where we have corpus-based chatbots. These could be information retrieval-based or based on learning some sort of sequence transduction. And here we come to sequence transduction, where you sort of see that you have an incoming sequence that says, how are you? That's a question. And the output ends up being a string called I'm fine. The model up there is an LSTM encoder-decoder model. Right. And that has a hidden state. Okay, good. What we're going to do is actually talk about frame-based dialogue systems. Okay, we're going to see frame-based dialogue systems. So essentially, a lot of the tools that are out there are frame-based. So this essentially says you want a knowledge structure representing the kinds of intentions a system can extract from user sentences. Each frame essentially has a set of slots, and slots can take on values. So if you take that as an example, show me flights from Boston to San Francisco on Tuesday, you want to recognize what the intent of this phrase is, which is show flights, and then pick out things in the slots, like origin city is Boston, the origin date is Tuesday, and so on. So when you do something like this, you need to do a bit of parsing up front. And here is an example of a parse of the same sentence, mapping the sentence to the slots that you need to be filled in. So this is an example of a task-oriented chatbot, and that's what we'll carry on. So the task-oriented chatbot for this flight booking system could be essentially a finite state system where it's sort of system-driven, and you're sort of setting it up to ask and follow a particular dialogue order, right? So you could think of it as a flowchart that's sort of been programmed in. And then you might want to also ask follow-up questions if you didn't get something right. If you wanted to do a destination city, you'd ask where you're going. So there are system initiative chatbots and there are mixed initiative chatbots, where a mixed initiative is where a particular user actually talks about it, takes the initiative for dialogue. Rasa is one such open source tool that's available. Competing tools are Dialogflow, and so what it is that there's a spoken language understanding that a unit that actually tries to make sense in terms of extract information and entities. So the natural language understanding essentially operates like the ears, right? And then there's managing the context of the conversation itself, which is the brain, right? So that's where the dialogue management happens. And then is to generate a response, which is the natural language generation. So you can see that the natural language understanding has two things that it needs to do. It needs to get the intent of what the incoming sentence is and what the entities are, right? So we need to figure out the intent and what the slots are. So in this example, the entity ends up being tomorrow. But the thing is, we'll sort of see why dialogue handling is sort of essential. In sort of system-driven chatbots, you had a lot of state machines. And in the next couple of slides, we'll actually see that these state machines can get fairly complicated. So this is one example of a state machine. And as your conversation grows or as your application grows, this is an excellent case for actually having machine learning manage it. So this is a state machine for a dialogue system where it's kind of massive. You really don't want this to be happening, right? So that's where Rasa actually, after its NLU, it takes the entities and actually has a dialogue context manager, which could be something like an RNN. It's taking in features and predicting what action it needs to take next in order to generate a response, right? So that's the end of the talk. And that was lightning fast. Thank you.
Thanks, Aanchan. I realized I made a mistake. You didn't get a chance to introduce yourself, so can you do that, please?
Oh, yes. My name is Aanchan. I work as a software developer and a machine learning scientist at a brain health company. So I'm employee number one with a lot of help from a few part-time people. So we're putting a product together.
Cool. All right. Yeah. Questions for Aanchan?
Yeah.
From previous discussions, I know that you have been trying to build a chatbot at work. Can you maybe describe how that's going and how successful and difficult it is?
Right. So one of the things for brain health that's important is to actually get you to sleep and wake up on time. There are actually chatbots on the market that help you do that. So what we've done is we're using one of those products as a baseline, and we're using Rasa Core. So Rasa that I talked about, I don't know if I can. Rasa that I talked about is actually an open source Python-based tool, which does the same thing as Microsoft Louise or Google Dialogflow, except that you know exactly what's going on under the hood. So I would encourage anybody so these are extremely good for task-based chatbots, right? So it's under development, but it's easier than I imagined it would be because of tools like this that are available.
I saw a video on, I think it was Google, where they were booking restaurant tables with a bot.
Yes.
Booking with a real human.
Yes.
And it just struck me that there's something wrong here. Like the human wasn't aware. They're so good, the human wasn't aware as a bot.
Yes.
So are there any rules on that? What are your thoughts on the ethics of that?
The ethics of taking away someone's job?
No. I mean, should every bot have to announce I'm not human at the beginning, right?
Well, that's like the holy grail of AI, right? I don't know. So you'd want to be able to mimic a human being, but I don't know. Some of them can actually tell that you're talking to a bot, whereas some can't. I don't know. That's a tough question to answer. Back when ELIZA was made, this was in 1979, right? People thought it was a real person, right? And this was just a rule-based chatbot that was just giving back answers, right? And it was just like transforming what you said. So you can't. I mean, I don't know. It's a difficult question.
So for like image categorization, say there's a competition that runs every year to sort of work out what's the what are the best algorithms, what's cutting edge. Is there similar sort of competitions for chatbots, and like what's the kind of progress that's been made recently with the rise of deep learning? Has there been sort of really rapid progress, and like have you seen similar kind of results to how you've seen ImageNet competitions?
Yes. So one of actually this was part of another talk that I made. So Amazon runs an Alexa chatbot competition, and the Montreal Institute for Learning Algorithms actually had an entry there, and they have a really interesting paper where they're actually ensembling like 150 different chatbots in order to generate the next best response, right? So this is completely open domain. They didn't win it. Apparently someone did better, but they were using reinforcement learning for it, which I thought was pretty neat, which is, can I pick from candidate models what the response is going to be so as to maximize a future reward, right? So it's immediate versus future reward kind of thing. So should I present a news interest article right now, or should I present, like, ask a question, right? So there are those odds to sort of take decisions between. But then in just closed and open domain question answering, you have tasks like something like there's a standard question answering task called the Stanford question answering task, and there are many more. So if you go to ACL or any of these, it's amazing like how crazy deep learning is doing as far as like just the task of question answering goes. Right? So Salesforce has like a ton of work on this, which is like, yeah. So it's getting more and more amazing and scarier. But are they coming into production? Is en masse, are people interacting with this day in and day out and feeling like it's a great thing? I don't think so. I don't think there's enough great customer experience out there. Yeah.
Oh, hey. Would you consider what Raza is doing approximating the finite state machine, or is it doing something else entirely?
It's approximating the finite state machine. So there's actually, I didn't know there's been a lot of work on dialogue prediction. And actually, a lot of the material I took out of here is from Dan Jarafsky's new book, especially this diagram. And dialogue state tracking has been more in the academia and now coming into production. So that's why you have these tools like Dialogflow and Rasa actually doing these things. So the dialogue state tracker is, in a large way, overtaking the conversation handling. And yeah.
What's the name of that book?
Spoken language processing.
So for Rasa, there's a recurrent neural network inside it. How do you evaluate success when you're training that model? Are you relying on something like Mechanical Turk or some human to create all this training data?
So that's a fairly loaded question in two parts. One is, what do you do when you don't have enough training data? And one is actually the evaluation, right? So in order to get training data, yes, one could use something like Mechanical Turk. Facebook has a really good tool called Parlay, which actually makes use of the Mechanical Turk libraries and allows you to set up question answers so that someone actually reads a passage and actually presents. So one of the problems with question answering is you never have parallel question answering pairs. So like Parlay, what it does is it'll present a passage and ask the Turker to actually present the question and the answer at the same time, right? And then you can have inter-annotator agreement. Parlay, the other thing it does is also allows you to evaluate models, right? So that's the other thing you can do. Third thing, when you don't have enough training data, Rasa also comes with an online training feature that, like, automatically through multiple interactions can generate what are called user stories as you go along, which is examples of conversation flow for the LSTM. So those are varying shades of the same question.
Tell us a little bit about the state of the art in terms of, so it looks like for a task-oriented dialogue, maybe it's doing quite well. So what is it very good at, and what is the frontier of where it's still struggling? Based on your own work, if possible.
So I think closed domain, task-oriented chatbots, you can construct fairly decent ones with the tools that are out there. Anything that's open domain, right, where you want us to, like humans have a conversation, that's the holy grail. But surprisingly, even question answering itself can get very domain specific, right? So you can have customer service question answering versus tell me a story kind of question answering, right? So question answering itself is where the frontier is, I think, at the moment. But then that frontier is also sort of bleeding into open domain, like social, like proper chatbot. So that's what I've seen from conferences. I think that's where the greatest challenge lies, and it's hard from being solved.
Okay, is there a lot of people using GANs or?
Yes. So one slide that I skipped over is, or maybe I just did blah blah over, is handling multiple turns with, so sequence to sequence models, right? These don't see any conversational context, right? So like it would do well on one question and giving the answer to that next question, but does it give the best answer given the dialogue conversation up till now? No, it actually does pretty badly. And that's where you look for more powerful modeling formalisms. And GANs have actually been used there. So there's been some really cool recent work in using GANs to actually allow for seeing and generating responses from like wider contexts. Oh, it's still doing the timing thing on it. Yeah.
I think that's all the time we have. Cool. Thanks, Aanchan. So I'm going to try to fix the rest of my mistake here and let Matt introduce himself as well.
Hi, everybody. My name is Matt. I helped organize the meetup that's happening tomorrow. I just kind of want to give another shout out to get the word out there for that. Bill, who's in the room, is going to be presenting on a sequence-to-sequence competition. Is that right? Yep. So that's kind of similar to this. So yeah.
And my name's Andrew Brown. I'm a local data scientist working at a startup and your host for tonight. Sorry I didn't introduce myself sooner.
We got the.
It's down at the bottom.
Oh yeah.
Can you click the mic a little bit on the other side? Your head and natural point.
Am I? Oh yeah, I see. I get it.
Oh, I see. Yeah.
It's like a really.
Obnoxious.
Yeah.
Obnoxious.
Look at it. There you go.
And I'm
you can hear me. Yeah.
And to start the timer, just hit that, but introduce yourself first.
And then I can start. Well, this is like my introduction slide anyway, so I can just. Is it gonna skip it if I start it?
It'll give you 20 seconds.
Okay.
30 seconds.
I can introduce myself in 30 seconds. Okay. So same slide deck as Aanchan. So good taste. Good taste. Yeah, good work. Nice. Okay, so hi everyone, I'm Mike Irvine. So I'm going to be introducing making better decisions with Bayesian networks. We're going to shout out every time I say Bayesian. And I work in basically applying sort of modeling and data science methods in public health as part of my postdoctoral research at UBC and the BC Centre for Disease Control. And at some point, it's going to skip over. Okay, so what are Bayesian networks? So the idea is essentially you have some data and you want to sort of decompose this data into a series of conditional relationships between these things. So you can kind of think of this as like a causal network, or maybe kind of causal conditional. So for example, this network over here, if the grass is wet, well, it could be that it's been raining, or it could be that you've been using sprinklers. But if there's sprinklers, then it could also be a relationship between if it was raining and whether you use sprinklers or not. So you can build these kind of relationships together. So what can they do? So Nate Silver has successfully used them to sort of predict the outcome of the 2012 US statewide elections. Don't talk about the other election. It was used predominantly a lot in Microsoft products. So we have Bayesian networks to thank for Clippy. And sort of counterfactual modeling you can also do. And there's lots of examples in clinical detection, kind of risk calculators, understanding what your risk is of, say, a sexually transmitted disease, and also clinical prediction rules. So some of the advantages of using it, well, it deals with missing data quite well because we could just marginalize over the probabilities. So we could just take that red node out. We can look at causal relationships. So say we know that there's definitely a relationship between these two things, we can impose these relationships in. We can also look at multiple predictors. We can just construct one single network, and we can have a look at these two orange predictors. We can also understand something about causal intervention as well. So if we switch on and off this intervention up here in purple, we can understand how this probability flows through the network as well. So some key concepts. So one of the main things is the idea is to try to sort of decompose the probability of two variables separately conditioned on a third variable. So for example, if we have a relationship between x and y, then you can decompose this into what's the probability of y given x multiplied by the probability of x. And so in this way, you can start to build up more and more kind of complex networks from these kind of simple rules. There's a few other sort of things. So as an example, we can think about if your car doesn't start, what could be you don't have any gas or if your battery's dead. But if you haven't checked whether your car's starting or not, then having no gas or a dead battery, they're independent of one another. But once you actually check whether your car's started or not, then there's dependency between those two things. So this is an example of Bergson's paradox, which is different to Simpson's paradox, and I will explain that over a beer afterwards if anyone is interested as to why those two things are different. So again, this is a way of sort of understanding how these kind of relationships, these causal relationships, can be built up. And naive Bayes is an example of this. So there we just impose a very simple network structure. The idea is we have a single output that we're trying to predict on, and then we have a series of conditionally independent inputs, which is this naive assumption. And then from there, we just build up into this relationship that I was talking about before, where we just take all these conditional probabilities, and we can just write down something called like a likelihood, and then that's our score in which we can then apply it to data in order to sort of build up what the network should look like. But in general, you want to sort of understand, you want to sort of learn the network from the data. And so the way you can do that is, well, there's two main methods. You can use a scoring-based method or a constraint-based method. Scoring-based is essentially you propose new links in your network by either deleting them or removing them. And if it's a valid link, then you check that score against your original network. And if the score is somehow better, then you apply that new network. And you just keep going until you reach some stopping criteria. So as an example problem of this, let's say there's some students in a class. So the class has a certain difficulty, low or high, and there's an underlying intelligence of the student, low or high. And the intelligence depends on their SAT scores, but the grade you get in the class will be dependent upon the difficulty of the class and the intelligence of the student, and then whether you get a good letter of recommendation or not is dependent on that grade as well. So you can see intelligence, or say SAT might look like it's conditionally related to letter, but actually they're independent. And so I wanted to experiment this, so I used this R package called BNLearn, which seems to do a pretty good job. So I generated some data from this model that I presented on the last slide, and then I was using this kind of learning the structure using a hill climbing method with AIC score. I fit the network to the data, and then I estimate the error structure, just looking at the Hamming distance, so how many links do I have to change in order to get the true network, and then estimate the probability of, say, getting a good letter of recommendation given the student's intelligence. So varying this over sort of different data sizes, going from about 100 to 1,000, you can see that eventually I'm sort of basically getting one or two links wrong. And then if we look at this kind of probability of getting a good letter of recommendation, given the underlying intelligence, we can also see this is starting to converge after getting a good amount of data, around 1,000. But you can do something fairly well with a small amount of data, which is one of these advantages of using these Bayesian methods. Okay, so how do they generally perform? Well, this is taken from a review paper from 2016, looking at sort of various sort of clinical prediction rules. So we have things like sort of various cancers, like prostate cancer, brain metastasis. I shouldn't say that. It's hard to say when you're talking quickly. There's also minor head trauma,
adverse events and jaundice, and they're doing fairly well in terms of the AUC and accuracy score. But I couldn't really find anything that was comparing Bayesian networks to other methods, and I think that would be kind of interesting. So kind of wrapping up, one of the main advantages of this is it provides a framework for a model with sort of transparent reasoning. You can see why a model is making a prediction because it's associating these variables together to say there's a probability of an outcome because of these other outcomes. It's easy to model these scenarios. It's easy to calculate complex probabilities. So if you have some evidence and you want to calculate some complex result, and hopefully to provide insight. Structured learning in general is hard, but you can impose as a blacklist or a whitelist. You can impose links, or you could say these links definitely shouldn't exist. You can also generalize to non-categorical data using a sort of like a Gaussian framework. You can also make it more Bayesian by incorporating some of your prior knowledge as well. And it seems like they work best on these kind of noisy data, sort of small to medium data sets. Ideally, so the classic example would be in a clinical setting. And I also have a link to the lovely R code in case anyone likes using R and wants to have a look at that. So thank you. That's speed. Yeah, it takes a lot. It's a workout, isn't it? Yeah, it's good.
Thanks. So when I made Bayesian networks, sometimes the causality arrows are not going the way that I would expect.
Yeah.
And is that just always going to be like that, or is there? I mean, aside from blacklist or whitelist, is there?
Yeah. So for like I didn't talk about it, but there's the other structure, so a constraint-based method. Oh yeah. That's good. So like a constraint-based method would build up a network structure and would have some of those links, wouldn't have an arrow, because it's using this kind of mutual information criteria or something to work out there's a relationship here, but I can't work out what the causality is. So you can go in afterwards and impose it. So I was trying to work this on a data set which had, say, over 100 variables, and it quickly became a difficult task to actually go through the network and try and sort of decide, okay, does this reasonably depend upon this, or does this reasonably depend on that? But for like a hill climbing method, you could kind of get them swapping around sometimes, depending on what's going on in the network. But there's this do calculus which tries to impose causal relationships based on data, so you can sort of read up on that and sort of you decide. But most of the packages don't seem to sort of take that into account. I think it seems to be slightly more theoretical than.
You used a phrase in passing that I've heard in this context before, and I've never quite understood exactly what it means, and it seems to mean something more precise than its everyday usage, and that is explain away. Can you explain what that means in words of one syllable?
That was the this method, this idea. Yeah. So the idea is that so if I haven't started my car yet, then if I know my battery's not dead, or if I haven't seen whether my car's started or not, then whether I have no gas or not, or whether my battery is dead, are independent of one another. But as soon as I know that my car doesn't start, and then I go and check the gas tank, and the gas tank is empty, then I know something quite strong about whether the battery is dead or not. So by knowing something about one part of the network, you're sort of increasing the conditional probability to be much higher for something else. And so this is something you can pull out quite easily from the network to say, like, if I know these two things, conditioned on the fact that I know these two things, what's the probability of, say, the battery being dead? So Bergson's paradox is to do with this kind of structure. So an example of this would be in, say, college. If college admission is based on people who are sporty or people who are intelligent, and you could be kind of either, and you look in the subpopulation of people who have gone to college, then you would find a negative relationship between people who are sporty and people who are intelligent. And that relates to that's the example of Bergson's paradox.
Okay, if you have like what's it called, collinearity in the attributes, how does it impose like a latent relationship to those two, or
if you have sort of collinearity between sort of two variables, and then is it going to sort of try and impose a relationship between those two?
Yeah, to like a hidden latent variable. Does it?
Oh, if you have a hidden latent, yeah, if you have a hidden latent variable, then these things might start to get a little bit trickier in terms of trying to resolve them. So the networks I presented were for sort of variables where at least you had some observations for, maybe some you didn't, but you could kind of work your way through them. If you had like a latent state, it's generally more difficult. But I mean, so Bayesian networks are in a subclass of things called graphical models, where you would so like say a hidden Markov model could be put in within the framework like this. I don't think that really answers the question, but so.
Going back to your last slide, you had something making that more Bayesian based on prior knowledge.
Yeah.
What does it mean? I mean, like, what is more Bayesian, and how do you incorporate prior knowledge?
So it's interesting. So it's like Bayesian networks are called Bayesian because they're using Bayes' rule to build up sort of like these conditional relationships with this kind of network structure. But often when people talk about Bayesian inference, it's because you are taking in some prior knowledge, which you are calling like a prior, and then you're applying that to your likelihood, in which case this would be like the network model, in order to get like a posterior, which is based upon what your previous knowledge is and what your current knowledge is. So then what I've presented here isn't a Bayesian inference because we haven't given it any prior knowledge, but we can do this because we're just sort of updating essentially what the scoring function, this likelihood, looks like. So for instance, if I know that two variables are very strongly correlated, and I can say, this could be my prior data, say, and then I look at some new data, and I can update all these probabilities based on this new data, and it would give me something that is in between this prior information and what the data is telling me.
Is it just giving more data, basically? Is it just bringing more data for training, or?
It's a way of sort of being able to sort of cope with maybe if you don't have small data, or maybe there's certain parts of your network you haven't really observed before, but you have had sort of previous data sets and you've looked at this elsewhere. So in a clinical setting, you might know something about certain outcomes based upon different symptoms, or say getting like a positive or negative X-ray or something like that. You would know something strongly about that, and so you'd want to kind of put in that information before you see like new data, which might only be, say, 100 patients or something. So you'd want to sort of be able to sort of incorporate some of those details in. But eventually, I forget, there's a theorem that basically says, as long as everything's okay in the network and the data you're using, at some point the data is going to overwhelm the priors, at which point you are just basically looking at the likelihood.
So we're looking at Bayesian networks and deep learning networks, totally different things, but they're trying to do in some ways similar thing. Is there some kind of continuity in the design space? Like are there networks in between? Can you comment on that design space at all?
Yeah, so there's some exciting stuff that's happening with variational Bayes methods, which is essentially, so you normally write down a likelihood before, and in order to do this kind of Bayesian method, you have to do sampling from this. Because you have to kind of approximate this amount, so you have to do sampling from it. There's a way of sort of converting the posterior where you have to do sampling into something that you can just evaluate immediately, in which case it turns the whole problem into a stochastic gradient descent problem, essentially. So this is what variational Bayes tries to do. There are these really nice methods basically being developed. There are these really great probabilistic programming languages that are sort of coming online where they're trying to actually do Bayesian deep learning networks.
Hey, I was just wondering, is there a way of adding regularization into a Bayesian network?
I would say like your prior could be your regularizing factor. Often like when people talk about regularization in a Bayesian context, they will try and sort of do that using a prior.
Right, and how would you do that in the discrete case?
Yeah, it's interesting. So you would have to, for like a categorical. I've seen it done for like continuous variables. What sort of a prior would you use? It must exist. I can't think of the top of my head.
It's like a half country on the variance.
Yeah, that's one of the ways you could do. You could do like spike and slab thing, like methods as well. So I could say like, I could have a probability that I think that there's no link whatsoever or something, and I could vary what this prior probability would be. Yeah, so you could incorporate something like that would then make the network more sparse or increase. Yeah.
You mentioned that on the last slide that Bayesian networks are quite effective for noisy data problems. Can you give other use cases where these networks are effective?
So yeah, I had a bit of a look around, and like it seemed like people like them when you wanted some kind of model transparency. So this is helpful if you want to do, say, counterfactual modeling, where you want to manipulate some part of the network or to say, so for an example, there was one looking at different rental investment portfolios and you're trying to project the future. So under there, you have some data, but then you've built up a structure of a model that is somehow kind of representing causal relationships. So I can switch on and off a certain part of my portfolio and see what the end result is of that. And then, so examples for, say, the US statewide elections, I think it worked quite well as this Bayesian network because there are certain things you're asking people about that are going to be sort of like strongly related to everything. So you could kind of build up what maybe some of these biases, which are coming from just polling, which party you're going to vote for. You can maybe sort of somehow incorporate what some of these biases are, people are saying that, and what states they're in by using like this kind of network structure. There, I think it may have been more of a hierarchical structure where you have some underlying rate, and then you're going up, and your network's going up into the different states. Then you maybe have some sub variables there as well.
So what would a package buy me? So with all these nodes, how do I construct them a priori in terms of the reasoning model and the paths that I walk through? Or do I just throw my data in and it figures out what the reasoning paths are and the dependencies are automatically?
Yeah, so one of the big differences between this constraint-based approach is that it will sometimes not be able to determine the arrows for you, and so you'd have to go in afterwards and like sort of manually go, okay, I think this relationship is this way around. And then there's, with hill climb, it's always going to give you your arrows, but the sort of simplest thing that people seem to do is they'll just have a whitelist, which is, I definitely know these arrows should be here, and a blacklist to say, I definitely know these arrows should be here. It seems like that's where people sort of try and build in their constraints. Because once you have like a structure, you can then fit that structure to the data, and it might end up sort of saying this variable doesn't actually really depend all that much on it. So the arrow could be very weak, basically. In other words, you can still kind of get that. But say there's an arrow there, but it's actually very weak for the data you have.
All right, thank Michael.
And you got a green light now?
Check. Yeah? Okay, sorry. So like I was saying, my name's Robin. I work for AgFunder. I'm head of engineering. AgFunder is a small VC focused on food tech and ag tech, and I'm head of engineering there. I also have my own company here in BC, Pathway Intelligence. And my son, Chauhan, was kind enough to help me with this presentation. So I'm going to be talking about OpenAI DOTA 5. Begin. Okay, so OpenAI is a nonprofit research company. The goal is to promote and develop friendly AI to benefit humanity as a whole. They expect that AI is coming anyway, and their idea is to empower as many people as possible with AI. It was founded in 2015 by Elon Musk and Sam Altman of Y Combinator. So this presentation is about their DOTA work. DOTA is Defense of the Ancients. The first DOTA was a multiplayer online battle arena that kind of started the craze.
It got taken over by another company in Valve from Blizzard, and Dota 2 is played by a huge amount of people every month, and there's a lot of betting that happens, especially in Europe. So Valve created an API for a bot level API for Dota, and that's what their OpenAI's bot accesses. It's not pixel based; it's based on the game elements, so it's quite different than say what was done with the Atari or AlphaZero work. There's some simplifying restrictions that they made to simplify their work. This is the network that they use this is the policy network. So this chooses the actions based on the inputs from above. You can see there's a ton going on here, but basically the different units, modifiers, abilities, and items, pickups, and things about the landscape, and all the different types of actions are coming out the bottom. The key component there is on the left is the LSTM. So this is a simplified diagram I made to help you understand what's going on. The LSTM is kind of the heart of the thing. It's a one-layered 1024 unit LSTM. There's also some observations that bypass the LSTM, as you can see here. Unit attention and valid actions. So there's different types of layers, but there's no exotic layers here. There's kind of the basics. Fully connected, ReLUs, embeddings, concat slice, max bool, softmax. The observations, remember, they're not planar. It's not in taking in the pixels. It's taking in discrete attributes that the bot API is providing into the network. So each of the 5 agents, this version is 5 versus 5. That means 5 players are collaborating at once. Each of the 5 players has their own network, their own LSTM. There's no communication between the bots, which is key to the multi-agent aspect. So this is the training system. This is a big innovation that they added this time around. So it's called Rapid. Many GPUs collaborating. There's rollout workers and evaluation workers. The GPUs are connected using high-speed interconnects. And so this is a distributed training system that's key to some of the performance. The rewards were shaped. The raw rewards from the game are too sparse. So they made synthetic rewards having to do with each hero's performance, subtracting the enemy score and the condition of the buildings, and then rewards towards the end of the game are scaled down. So action selection is a key component. The available actions are piped in and dot producted with the output of the LSTM through a fully connected layer. And then softmax and sample and argmax, depending on whether it's train or test. So that outputs the specific type of action. And there's actually many action outputs. We'll look at the other ones. So one key action output is the target unit. So you can cast a spell on, say, an enemy or maybe healing on a friend. Is that correct, Kieran? I actually haven't played the game. He's my game consultant. And so all the attributes of the units are piped in to select which unit we should be focusing on at this moment. So you can see there's other types of action selections to action elements as well. We talked about select action and target unit, but there's also offsets, moves, destinations, and delays. So all these together can be considered the output of the network, the actions. And they work in a similar way. So this is a really key component of the Tau, the team spirit. So basically, in the beginning, the Tau is set to make the agents selfish. They're trying to maximize their own reward. But as training progresses towards the end, they become more team spirited. They are focused more on the team reward. So they actually end up playing in a selfless way. It was trained with what's called PPO, Proximal Policy Optimization, which is kind of OpenAI's flagship model-free reinforcement learning algorithm that they came out with in a paper last year. And I'm not going to get too much into the details, but basically they clipped the loss function in this way that makes it's a policy gradient method, but like a lot more efficient than vanilla policy gradient. So you can see this is last year's 1 versus 1. They did 1 versus 1 bot last year. That took 4 months. This is the 4-month performance, a relative performance from it rose that much. Here they showed some curves from, and this is just in days, where the sparse reward and dense rewards, you can see dense reward is, all right, that was fast. In terms of the how much compute it took, I will expect that they're going to be somewhere over here. They haven't released the exact position yet, but their 1 versus 1 was down here. This is a lot of compute. This is a very expensive project. On the other hand, here's a GCP employee saying that it's within reach. So my take on this is the things that were kind of innovative here. the rapid, their distributed training, the teamwork with the Tau, I think that's really cool. The net design actually is the human knowledge. And then the single layer LSTM is just so simple, it kind of surprised some people. So I think the formula, the AI formula used here is this hand designed network, the teamwork annealing with the Tau, the LSTM RNN, the general purpose RL, and then this brute force. It's very similar to AlphaZero in terms of that formula. It's kind of discouraging for people who really think that HRL and specialized approaches are more important. The impact, OpenAI has bragging rights about this, I think. It's the biggest multi-agent collaborative competitive result mix so far. It might provide a roadmap for the StarCraft. I don't know what it'll do to Dota or game AI jobs. It's not AGI, so we don't have to talk about that. So they're actually playing, the huge competition is going to be in Vancouver on August 20th. They're coming here. You can buy tickets for the low price of $500. So I'll be watching online. But it'll be streaming on Twitch here, so that'll be quite historic, actually, to watch that Twitch. And thanks to Kieran for memes and for advice on the game.
All right, any questions? All right.
So you mentioned that there are like 5 agents controlling 5 bots. Are all of those trained in the same way, or are there different agents trained, for example, to different types of heroes or different roles within the team?
Yes, as far as I know, so there's limited information out so far, but as far as I know, they are trained on different heroes, and they're using a subset of heroes, that the system understands how to play optimally on. So they've been removing some of these restrictions actually just even last week. All this work is super new. It was just published last month, but the whole details weren't published. So, and then some restrictions were removed last week.
And I just want to confirm, because you said it, but I want to confirm that those agents, they are not sharing their intentions with each other. So
they're not
saying,
communicating.
like, I'm going to do this, you can include it in your planning.
No, they're not communicating, but they would see each other through the observations, as much as they can see through the game, but they don't have communication.
Yeah, but it means they only see what already happened. They don't see the intentions.
Yeah,
like
that's
that
right.
Somebody is going to use.
There's no central controller. There's no central strategy or
Okay.
any central piece.
Okay, interesting. Thank you.
My question is kind of continuation for the previous one. Do you know if the agents, they keep retraining during the game, or is it like pre-trained LSTM layer and it doesn't change during game?
Yeah, so if you look here, it says it's pushing data every 60 seconds of gameplay. So my take on interpreting that is that it's doing a training step every minute, and it's adjusting the policy every minute as it's rolling out all of these in parallel.
So in a way, it's actually learning based on the other team performance and what they are doing. In a way, because it gets new data every 60 seconds.
Yes, right? But it's self-play, so the other team is also itself.
But in that game, in Rogers Arena, they will be playing real
Yes,
humans,
when they go
right?
to perform, they're playing against some other opponent. But as they're training against its own replicas of itself.
No, I understand that, like during a training, but like during the game, like actual game against humans, are they going to be doing that, like retraining?
Yeah. I don't believe they would do any updates or training during playing a human in a match. Yeah, I don't think they would do. I think they would just use what they train in. They train like 900 years per day or something. It's kind of crazy. So I think by the time they show up to the tournament, I think that's probably quite a bit of training.
I'm not familiar with the game, but is it discrete like a board game, or is it continuous movement? And can you talk about the time discretization, like what speed are action decisions being made?
Yeah, that's a really good point. So I think some of these are more continuous, like these sound more continuous, and some of these are discrete. But continuous, it must have some resolution too. And I don't have the exact answer for you, drilling down to that. And sorry, the second part of your question was?
Just the speed of the frequency.
The speed, right. So they actually turned down the speed for the latest update last week to make their reaction time, I think, 200 milliseconds, which is more on the order of what a human would do. Because some people were saying that, oh, you're just winning because your bots are faster because they're computerized. So I don't know if that was the motive, but they increased the reaction time. Before it was down, I think, 80 milliseconds or something. They were saying no human could respond that quickly, something like that.
So 5 times a second.
So there is some sense of limit to how fast it responds.
Did they give a rationale for why the teamwork annealing was needed instead of just starting out at a certain tau?
Right. I don't think they gave a rationale for that, but I mean, long story short, you always want every agent to be able to perform well on its own. Like if all the other agents die, it should still do well. And then it also seems like teamwork is a more sophisticated concept, a more subtle concept. So it might make sense to master that after it's kind of like almost like a curriculum learning type approach-ish. I don't know, that's the best answer I have right now. Any other questions?
Anyone else? Yep.
I'm curious to hear a little bit more of the philosophical undertone that you implied with AGI.
Okay, so I mentioned here that because people, every time you bring up AI or like these things hit the news, people are like, oh my God, Google solved Go, soon they're gonna take over the world. And they're like, well, so these systems are, to this audience, maybe it's a silly comment, but I'm just saying for these types of systems, they're so specialized for the domain. Like this network here is highly tuned for this domain. You try to attach this to some other domain, it just won't make any sense. But what you might get is you might look at this and say, well, what heuristics were used to design this network? Maybe we could understand those and apply them to somewhere else, but you're not going to apply specifically this. So this is I don't see this as a big step towards AGI. I mean, like, if you look at these games, it might be like, oh, this kind of looks like a world, and it kind of looks like people walking. Maybe, but there's a huge gap between this type of simulation and any kind of real world. So I just want to emphasize that point. Does that answer your question? Thanks.
We've got a couple more minutes. Anyone else? All right.
So I'm very interested in this topic because I do play Dota from time to time. I'm just wondering if you know kind of what the response from the community is about this. Like, are people like really embracing AI winning, or I don't know, or like to your point, game AI jobs? Like, what are people's thoughts on that, or what are your thoughts on that?
Yeah, that's a great question. I don't know officially. I can't say I have the temperature of the Dota community. I'm not really in it. I'm more in the RL side, and I'm just learning a bit about Dota to get into it. But let me see. I think OpenAI is not expecting necessarily to win this tournament. This work is very new and kind of untested, the 5 versus 5. The 1 versus 1 they did earlier is actually, I think, a lot more tested, but this is kind of untested. So I don't think they're confident they're going to win. I think a lot of people aren't sure they're going to win. But that makes it more exciting when we're watching Twitch. I would think that as these graphs get better, it's going to be kind of pointless to bet on Dota because you're not going to know, and the other side's using some kind of bot. So I don't. To me, that would kind of seem to want to destroy the betting system and go up in Dota. But maybe there's going to be bot versus bot, and maybe it'll explode in a different sense. In terms of the job AI, like I guess where I was going with that is, at first you might say, oh my God, everyone's going to add these AIs to their games, and there's going to be all these jobs for deep learning in these games, but once that advances and there's toolkits for this and it becomes a one-liner scripts, and then suddenly all those could disappear. So all the legions of people who are writing maybe rule-based AI are going to disappear. And so I don't know, over the long term, that might kill those jobs. I actually don't know. I just think it's an interesting topic. Does that answer your question?
Yeah.
Okay. Yeah, I just you've been working on reinforcement learning for a while. So what is it about this architecture that you think made it work much better than what was there before? So I mean,
What's better here?
I mean, what intuitions did you figure out from this that maybe you could apply in some other projects?
Yeah, so I wanted to highlight those with these stars here. I think the rapid distributed learning system is a big innovation. So that allows reinforcement learning to scale up to really massive size. So that means a huge amount of training in a short time. The teamwork with the Tau, I actually messaged the OpenAI guys on a forum, but they haven't got back to me about some of these details. I guess they're busy. I think the teamwork with the Tau is so simple and so elegant. Few things here are very simple and elegant. The single layer LSTM, it's so simple. Like, I mean, there's so many papers out of DeepMind about very crazy architectures and methods to solve these similar problems. And here they just bypass all of that and just made a very simple method. And some people might say, oh, it's just brute force. That was their solution here. But I think the Tau is a huge deal. I think Rapid's a big deal. I think the net design, the way they design the network, that is the human knowledge they baked in. They understand the game, and so the humans constructed that network. So that's kind of it's not cheating, but it's definitely not AGI when you're designing your network. So they design that with experience and with knowledge of the game. Yeah, so I think in some ways it's exciting, in some ways it's disappointing because like all this cool research, like I'm saying out of DeepMind, you want to find some new conceptual stuff, and there's not a lot of conceptual stuff here, but it's a lot of food for thought, and it's a good data point in terms of how far can you get with these fairly vanilla methods. Like they're using PPO. PPO is a general RL. PPOs don't specialize for any of this. PPO doesn't care about teamwork. PPO is nice, but it's not. It's so general, right? So that's the surprise I think for a lot of people as well.
I would like to address a question by Matt. So actually, all the community expects these bots to win the professionals. So based on the last year when they brought one-on-one to the international, and bot was initially winning all the professionals, and it took them like a couple of months before they started winning over that bot over and over. Because bot was not trained. So last year when they introduced this bot that played one-on-one, they produced it as is, and they never kind of evolved this bot anymore since that. So people expect something similar to happen now, that they train networks that will be playing really great and will be killing humans like 10 matches out of 10. But then in a couple of months, humans will see where the problems of these bots and will exploit it and will start winning 100% of cases.
Thank you.
Sorry, guys, that's it for tonight. Can we thank Robin again, please?